Today, we are diving into the completely invisible world of electrostatic fields. This is the fundamental force that's behind, well, everything from that static cling on your clothes to the tiny, complex microchips inside your phone. You've definitely felt it, right? That little zap you get from a doorknob on a really dry day. It feels totally random, almost like a little bit of magic. But what if I told you it's not magic at all? See, that little shock is what we call an electrostatic discharge. It's a real physical event, and it follows very predictable rules. It's just the result of a huge imbalance of charge, and the universe doing its thing to balance the books. And that is exactly what we're going to do in this explainer. We're going to give you the toolkit you need to understand and, actually calculate the forces at play. We're going to turn that mystery zap into a problem you can solve. All right, so here's our game plan. We're going to start with an idea, an intuition, then we'll build up to the actual math, walk through a real example, point out a super common mistake to avoid, and then finish up with your complete toolkit. Sound good? Let's jump in. First up, the invisible force field. Look, before we even touch a single equation, we need a really solid way to think about this stuff. I want you to imagine someone's in the kitchen baking chocolate chip cookies. Now, long before you can see them, you know they're there because you can smell them, right? That amazing scent just fills the entire house. And this is where it gets really cool. This cookie analogy maps perfectly to the physics. The cookies, they're the source of the scent, right? Well, that's just like a charge, which we call Q, being the source of an electric field. The scent itself, that's the field. Your nose, which detects the scent, is like a small test charge that we place in that field. And finally, how strong the scent is, well, that's the force that our little test charge feels. Now, here is the most important part of this whole idea. That cookie scent fills the room whether you're there to smell it or not. And the electric field works the exact same way. It's created by the source charge, and it exists everywhere in space, completely independent of whether there's a second charge there to feel it. The field is a property of the source itself. Okay, so we've got the intuition down. Now we need the precise mathematical tool to actually measure the force we've been talking about. So let's move on to decoding Coulomb's law. This law, which goes all the way back to 1785, is really the cornerstone of all electrostatics. It gives us the power to know exactly how strong the push or pull is between any two charges. And the law really just boils down to three golden rules. First, the force always acts in a straight line connecting the two charges. Simple. Second, the bigger the charges, the bigger the force. That's a direct relationship. And third, the force drops off really fast as the charges get farther apart. This is that classic inverse square law you might have heard of. If you double the distance, the force gets 4 times weaker. And here it is, the full formula. F is the force we're looking for in newtons. Q1 and Q2 are two charges measured in coulombs, and R is just the distance between them in meters. And that little symbol, epsilon naught, that's called the permittivity of free space. You can just think of it as a fundamental constant of nature that describes how easily an electric field can travel through a vacuum. All right, so we know how to calculate the force between two charges, but what about the field itself, the scent from our cookie analogy? That brings us right to our next section, from force to field. The technical definition is actually beautifully simple. The electric field intensity, which we call E, is just the force divided by the charge. That's it. You can think of it like a map of potential force. At any point in space, it tells you how much force would be felt per coulomb if you put a charge there. So its units are, you guessed it, newtons per coulomb. So let's bring it all together. The big source charge, our cookies, creates the electric field, our scent. Then, when we place a tiny little test charge, our nose, into that field, it experiences a force. The field is the cause, and the force is the effect. Okay, theory is one thing, but let's make this concrete. It is time for a worked example. So here's our setup. We've got a positive charge of 2 nanocoulombs sitting right at the origin. Then, 1 meter away on the x-axis, we have a negative charge of -3 nanocoulombs. The question is, what is the force that this second charge, Q2, is feeling? This is really just a two-step process. First, you just identify everything you know. We have Q1, we have Q2, and we have the distance r, which is 1 meter. Step 2, we just plug those values straight into Coulomb's law. And when we run the numbers, we find that the magnitude of the force is about 54 nanonewtons. That negative sign in the answer tells us the force is attractive, which is exactly what we should expect. And before we even touched the calculator, we had a good hunch about this, right? One charge is positive, the other is negative. And what do opposites do? They attract. So we fully expected the force on Q2 to be pulling it back toward the origin. The math just confirmed what our intuition already told us. Okay, now for a really critical tip. I mean it. This one idea is going to save you so many headaches later on. Welcome to what I call the vector gotcha. This is how you avoid the single most common mistake in all of electrostatics. So here is the trap so many people fall into. They calculate the size of the force, the magnitude, and then they just sort of guess the direction. Oh, it's attractive, so it must be negative. Don't do that. The pro method, the one that is foolproof, is to use vector subtraction. You always take the position vector of where you're measuring the field and subtract the position vector of the charge that's the source of the field. This little trick gives you the correct direction vector every single time. No guessing required. And there we go, your complete electrostatics toolkit, all in 4 simple steps. Step 1, visualize the field with our sent field analogy. Step 2, use Coulomb's law to get the actual math for the force. Step 3, understand the field intensity as just force per charge. And step 4, always mind your vectors using that field point minus source point method. By the way, everything in this explainer was based on the foundational principles laid out in Elements of Electromagnetics by Matthew Siddiqui. It's a fantastic book if you really want to dive deeper into all this stuff. So we'll leave you with this final thought to chew on. You now have the power to calculate the force from any single point charge. But what happens when you have multiple charges, say 3 of them, all influencing one single point? How would you figure out the total force? Think about it. Thanks for tuning in.